Let's do an example now, which will also help serve as a summary of our potential energy and our conservation of energy and our potential. We have an electron with an initial speed of 500,000 meters per second, and it's brought to rest by an electric field. Couple of questions. Did it move into a region of higher or lower potential? And what was the potential difference that stopped the electron? Let's make a list of the things that we know. We have an electron, so we know the charge of an electron. And we also know the mass of an electron. These are probably numbers you don't know off the top of your head, but you can always look them up. What else do we know? We know that the initial speed is 500,000 meters per second. For speed and velocity, I'm going to try and use a cursive V so that we don't get it confused with potential, which is an uppercase V. I'll do that one in printing. And it's brought to rest, so the final velocity is 0. And it's brought to rest by an electric field. Let's do a sketch to go with our list of given information. So if there's an electric field, it means we have that electron in between the plates of a capacitor. Let's put our electron starting over here at the left. And it ultimately ends up over here at the right with a final speed of 0. This is the initial, this is the final. So here's where it's moving, here's where it's stopped. If we shoot it from here towards here, and it slows down, well, that tells us that there must be a force to the left. There must be a repulsive force. If there's a repulsive force, that tells us that this must be the negative plate. We know that like charges repel. We know that like charges repel, so as it moves this way, there's a repulsive force to the left that slows it down. Okay, we've got those plates labeled. We know that electric field points from positive to negative, so the electric field in this picture points this way. And we know that the force on our charge, F equals Q times E. Let's just make sure we understand what's going on here. We know that our electron is slowing down. The electric field is to the right and the force is to the left. So the direction of F is to the left. The direction of E is to the right. And this makes sense in terms of our equation because the charge of our electron is negative. If there's a negative here, it means F and E have opposite directions. Okay, I know that's a recap of electric force and field, but it never hurts. Let's start to think about part A. Did the electron move into a region of higher or lower potential? So let's try and reason that one out. There's probably 3 different ways we can attack it. Any of the 3 ways are okay. So I know that my electron is slowing down. If something is slowing down as it moves, it has to be moving to a region with higher potential energy. And if you want to think about that, imagine a car being pushed up a hill, or a car glides up a hill. So if a car is going at some fast speed, starts to move up the hill and takes his foot off the gas, eventually it's going to slow down. So if there's no force pushing him up the hill, he will slow down as the car goes to higher gravitational potential energy. We know that potential energy and potential are related. U equals Q times V, which says that V is equal to U over Q. If our charge is negative, then a high potential energy goes with a low potential. And that's because the Q is negative. So if this is big and it's negative, then this goes to a lower value of potential energy. It's a lot below 0, so it's smaller. Okay, if you don't like that explanation, there is another way to think about it, and we can think about it in terms of relating the potential and the electric field. So we know that, why don't I switch colors for that one? We know that our electric potential is minus the integral of E dot ds. That tells us that electric field, because there's a negative sign right here, that tells us that electric field points towards lower potential. So delta V is minus the integral of E dot ds. So E points toward lower potential. And we've already established in our diagram that it moves in the same direction as electric field, therefore towards lower potential. Okay, and VF less than VI. So all that said, if you couldn't figure out part A from thinking about these things, you could actually go ahead and do part B. If it's negative, it moved towards lower potential. If it's positive, it moved towards higher potential. That's an okay strategy too. Okay, let's do part B next. So what was the potential difference? To get that part, we'll apply conservation of energy. So our conservation of energy says, so part B, conservation of energy. Conservation of energy says that the final energy of the electron is the initial energy of the electron plus any work done by non-conservative forces. Work done by non-conservative forces means friction and things like that. There is no friction, so that's zero. Our final energy is our final kinetic plus our final potential. And our initial energy is our initial kinetic plus our initial potential. Okay, potential energy or kinetic energy is 1/2 times m times velocity squared. Final potential energy is charge on the electron times the final potential equals our initial kinetic energy plus our initial potential energy. Okay, so the capital V's in printing are potential, the lowercase v's in script are speed. Let's start to solve for our delta V. So we're going to want to get our potentials on one side. QVF minus QVI equals 1/2 mVI squared minus 1/2 mVF squared. You can take your half m outside if you wish. You certainly don't have to. And at this point, you could also plug in that your VF was equal to 0. I think I'll leave it general right till I get till the end. I want to find my delta V, so I'm going to divide both sides by Q. VF minus VI equals 1/2 mVI squared minus VF squared divided by Q, and VF minus VI, that's the delta V we were asked for. So delta V then is 1/2 the mass of the electron times our initial velocity squared minus our final velocity squared divided by the charge on the electron. Be careful with your signs here. You don't want to drop negatives because you won't get the right answer if you drop a negative. That gives us that our delta V is equal to negative 0.712 volts. Okay, so that's a negative for our potential difference. If we'd had trouble in part A, we could have gone ahead and done part B, and that would have showed us that it moved towards a lower potential. As it is, we did part A first, and then this confirms what we expected to get. Let's do another problem. In this problem, we say that physicists often use a different unit of energy, the electron volt, and you'll do this as you get into atomic physics if you go onward with physics, with dealing with energies at the atomic level. 1 electron volt, it's abbreviated EV, is defined as the amount of kinetic energy gained by an electron after accelerating through a 1 volt potential difference. Part A is what is the conversion factor? What is an electron volt in joules? We know it must have a value in joules because it's defined in terms of kinetic energy. So let's just write down our definition of an electron volt. It is delta K. We know that delta K is K final minus K initial. when an electron is moved through a potential difference, that means VF minus VI, of 1 volt. Okay, let's use this. We'll write down our equation for conservation of energy. We'll try and figure out delta K if we know that delta V is 1 volt. So there's our definition. Now we'll start with our conservation of energy. Conservation of energy says EF equals EI plus work done by non-conservative forces. There are no non-conservative forces in our definition. Our final energy is final kinetic plus final potential equals initial kinetic plus initial potential. We know that potential is Q times V. You might notice here that I'm not, or you might wonder, why aren't I putting in a half mv squared for my kinetic energy? It's because my definition is given in terms of kinetic energy. It's given in terms of K, so I want to leave K in my expression here. I want to figure out what is delta K because an electron volt is delta K. So Kf minus Ki, and I'll bring my QVF to the other side, is QVI minus QVF. I could take my Q outside if I wish. And over here I see that I have Kf minus Ki, which is what I was trying to find. That's my delta K. So delta K is my charge. Remember, the charge on an electron is negative of the fundamental charge. Now I'm going to multiply my negative E in through here. And then I could take my E back outside if I want. So EVF minus VI. Okay, now I'll put in my numbers. E is the magnitude of the fundamental charge, 1.60 times 10 to the minus 19 coulombs, times my potential difference, VF minus VI, that was 1 volt, that was given. So 1.6 times 10 to the minus 19 coulombs times 1 volt. A coulomb times a volt is a joule, gives me 1.60 times 10 to the minus 19 joules. So my delta K is 1.6 times 10 to the minus 19 joules. That's an electron volt, so that's my conversion factor. Okay, next we're just asked to use this conversion factor. If we know a proton has a 5,000 electron volts of kinetic energy, what is its speed? So this is our kinetic energy. We'll say that kinetic energy is a half mv squared, and we'll solve for V. Okay, part B. I know that my kinetic energy is 5,000 electron volts, and that's going to be 1/2 the mass of the proton times the speed of the proton squared. First thing I've got to do is get my electron volts into joules, use that conversion factor we just found. We'll see that the electron volts cancel, and we're left with joules. That's equal to 1/2 times the mass of a proton, 1.67, times 10 to the minus 27 kilograms, times V squared. Okay, so that tells us that V squared is equal to 5,000 times 1.6 times 10 to the minus 19 joules divided by 1/2 times 1.67 times 10 to the minus 27 kilograms. And then our V is going to be the square root of that. If you do that on the calculator, I'm not going to write it all out again. You get 9.79 times 10 to the 5 meters per second. One thing to watch out for when you're doing these problems, these are little tiny particles. They don't have much mass, so they do tend to zip around pretty fast. So we do anticipate in general that those speeds are going to be big, but they're never going to be bigger than the speed of light. They'll never be bigger than 3 times 10 to the 8. If you get a number that's bigger than 3 times 10 to the 8, then there's a fair chance you forgot to hit the square root button. So just be careful that you think critically about those speeds when you're finishing problems.